Hello, everyone. Thank you for coming. My name is Riccardo, and I'm here to talk about stream processing, which is pretty nice and interesting topic these days. I'm being involved quite a bit in the past using actor model with Akka.net specifically. How many of you are familiar with Akka.net? All right, a few of you. OK, that's great, because actually, we're going to talk about Akka streams, which is probably the next generation, the natural organic evolution toward the stream processing using Akka.net. But I was working a project that it turned out that around 2 a.m. every day, there was a spike of 100% CPU consumption in a server. And of course, we receive a notification. And you don't want to wake up at 2 a.m. if something go to the server at the time. So we figured out that actually it wasn't nothing really wrong. It was actually his design. We have a very heavy calculation engine that was kicking in at 2 a.m. To do this processing. And because really the computation was like SIMD, single instruction, multiple data, the developer did actually a good job, really. They are more sophisticated parallel for each loop to process everything in parallel, and that was fine. However, a better approach would be to analyze the current resource consumption in your system, have something that adapt, and maybe consume what the resources that are available, maintain some sort of reasonable resources free for the server. So, and at that point, Akka.net stream processing was the best tool for the job because we're able actually to leverage this technology to processing the data and the calculation engine using just the threshold that he wanted, regardless the resource that was available. So at least I'm here to talk about something that I'm passionate about that I use in production recently. So the agenda will cover about reactive stream, of course, why we're talking about reactive stream these days. I'm going to introduce about reactive extension, not because reactive extension per se, but because I want to introduce a problem the reactive extension has called back pressure, which brings us then to the introduction of a possible solution, including the end also reactive stream with Akka streams. And of course, we have a code demo in the hand, code reviews. All the slides, code sample on GitHub, and if I forget to put the link in the hand, I'm going to tweet about it, and I'm going to give you the link. So the objectives are talking about how we can react when there are very high rate events to handle, and how we can compose this event from different sources in a very simple manner. You can even produce complex logic in a very simple declarative manner. Boring slide about me. I'm originally from Italy, but I'm living in Washington, D.C. for the past 10 years. I play with technology. I finally, after a year and a half of intense work, completed my book, Functional Concurrency in .NET, published by Manning. And this are my 2 pugs and my wife up there. Hi. All right. I want to just quick thank you to Vajif. He's now here, my friend. We talk about Akka.NET, Akka streams a lot, and actually he helped me out also to build the solution for what I have in production. So I want to thank him. OK, so back to business. Why reactive? Well, because these days we have a lot of data to analyze, right? And maybe we have to apply some sort of real-time decision to this data. I just put Google here, for example, just to have like an idea the current big data the company has and actually what can predict in the future. They're going to be more and more the normal case. Like Google I have a 1 quintillion, right? Which is a crazy number. So I like only just the last slide. It really said 15 billion gigabytes, which is quite large data set. So when to deal with a sort of huge amount of data, how are you going to handle this data? Think about if you have a big stream of data that keep flowing more and more data, more and more events, right? But what about if you have to make some sort of real-time decision? I like the example of the self-driving car, OK? Self-driving car have a bunch of sensors out. What about they receive the notification from the event outside, and to make some sort of maybe apply some machine learning or some sort of algorithm to make a real-time decision? How are you going to apply this kind of algorithm? So there are a lot of different expectations for how we build application due to this new modern way to have like a lot of data. We have a lot of mobile devices interconnected. We have multiple architecture, cloud computation, and so forth. And even in mobile devices that are all interconnect to each other, really build a huge and large vast of network online, right? So how we can create applications that are responsive and collaborative, right? So that's bring to something that is called data in motion. And data in motion is something that is keep moving, right, in motion, but is data in real time, which analysis most likely happen on the same data stream, right? And data stream in motion is mutable. So there are messages that may translate in other messages, by morphing or mapping to other messages. And the original message can never change, right? So that emotionally start by flowing itself in a pushing style. So really, it's really like a stream that you receive data without asking. It's just you receive the data. And because there is such a large amount of data, so there are three characteristics that define data motion. Is the three V's: volume, variety, and velocity. Because you have variety of data, a large volume, and of course, because we have systems that can be like thousands of systems online, and each system can create thousand events, so you really can create millions of data to handle. So originally, we have few characteristics that we can use to build a reactive system, which is event-driven, scalable, resilient, and responsive, which you can see in a slide here, used to create or to react to heavy load or when you have a lot of event in a system. And this is also something that can be used data in motion. And I spoke yesterday in my other presentation about reactive manifesto, but really we're going to see how we start from the reactive manifesto and we end up for something that is called the stream processing organization, which is the same vendor that declared last year that embrace the reactive manifesto or the proprietary that you want to have to build the reactive system. Actually, now they start this organization to prepare and at least to announce what are the characteristics to have a stream processing, a real-time stream processing. And I'm going to briefly spend 2 slides later talking about the actor model, which is full compliance to the reactive manifesto. And really, I think the stream processing is a consequence of the actor model, really is a side effect. Like, because we're going to see the actor model is compliant to reactive manifesto, you can build a reactive system with the actor model. Well, not just with the actor model, but definitely is my favorite way. And but actor model in the context of stream processing has some limitation. So I want to spend 2 short minutes. Somebody asked me a couple of days ago, there is a bit of confusion about functional reactive programming, so I decided, I'm going to take the occasion to speak here and create a bit of definition. So what is functional reactive programming? Anybody can tell me what is functional reactive programming? Anything? Because it's a pretty broad term, right? It's pretty hard to, well, not hard, but it's not easy to give a right answer because there is an academic side, which is talk about functional reactive programming intended for like the handling continuous, the event that continue over time. And then the other part of the industry, which is more like the how react to event in a more, I want to say imperative way. But and the problem to me is that with functional reactive programming, we have 3 terms, functional, reactive programming, and this word can be only combined and give different meaning. For instance, we have functional programming, which is a paradigm that treats computation as evaluation expression and avoid mutation, the change of state. And a quite interesting property, like such as immutability and declarative and so forth. But what's interesting about functional programming is that there are, when you program using reactive programming, you most likely use high-order operations such as select, map, filter, and so forth, which are come from the functional world. And there with I think the confusion. The 2 things I think complete each other, but they're different. However, a few years ago, Twitter published a paper which explained high level how they implement the backend system to be very reactive, and they call your server as a function. In this paper, Twitter mentioned how important and fundamental in the core was functional programming to implement the system in a very reactive manner. So that's, I think, where a bit the relation between also reactive programming and functional programming stay in. Then we have the reactive programming, which is responsive to stimulus. Something happened, and we have a stimulus that responds back. It's a bit ubiquitous, but there are, as I said, there will be of confusion because we use reactive programming using functional programming, and that's where the confusion starts, but there are two different things. Think about the classic example, the spreadsheet. You have a cell C value that is the combination of cell A and B. If you change one of the cell A and B, automatically C updates itself. This is how we react. And then finally, we have functionality programming, which is the more academical side, which treat event as an evaluation of over time. And it came from a paper in the 97 from Puladaki and Connor Elliott. And functionality programming really, anybody familiar with Elm, for instance? Browser language? Okay. A few of you. Well, Elm, for instance, is based on functionality programming. All right, so React extension. React extension is a framework, part of the Microsoft library, that was introduced to embrace the observable pattern. And what I like about the React extension that you can really build complex stream processing in a very declarative manner with a link style. Am I familiar with the React extension? A few of you, okay. So embrace the observable pattern. And it was so important that Microsoft decided to introduce it and make it part of the core for 4.0. There are two main interfaces, observer and observable. But the idea that you can create the observer class, they implement the interface, the observer, and register to observable as a subscriber. And whenever there's a change of state, a mutation, you receive a notification. But the real benefit here is this concept that we have the invert from pulling to pushing, okay? So we have event that push instead than ask. So if you remember the traditional for each loop in memory collection, you ask for data, but if something's not there, it's blocking. Instead, React extension invert from interactive to reactive. Instead to ask for data, asynchronously, they're going to send you data. So it's not blocking, which is a great benefit. So this is the interface, as I mentioned, observer. I have three main methods, on complete, on error, next. And observable, just register, subscribe with the observer, and return and a disposable to unregister the observer, so it stops to receive notification. A little bit the same concept going to apply to reactive stream processing later. So the reason I want to talk about React extension for the code sample that's coming shortly to show the problem is called back pressure that I'm going to do shortly. So the core key here that apply is the composition, right? Really, composition is the king. You compose operator, like in this case, as a sort of pipeline to create a query, more complex query in a very linear and simplistic way. And really leverage common types pattern, like in the link style. You filter your stream of data, you project your stream of data, you probably group by, and so forth. So you really can build complex, sophisticated query. And you can see the last two lines. All this composition result in asynchronous stream processing, so it's no blocking. So what is a stream, right? Well, it's ephemeral, which means a very short period of life, right? Events are transient. They come in and come out. And during the period of time, you can apply your transformation. And the problem is, though, that stream possibly, and that's actually where they probably arise, can be of abundant size. What does it mean? It means that stream can also be infinite. How you can handle that? And the problem is that most likely when you have a producer, they can be faster than a consumer, right? So here you have a React extension just to analyze a stock ticker. you can see we have the observable stream, something that I built in. I'm going to show the code in a second. You can throttle. We can group by stock symbol. And then we can select many for the group and subscribe to do some charting update, okay? So let's see the code, and let's see what's happened here. What could be the problem? Okay, so everybody can see in the back, this is a pretty large screen, right? So, okay. So the code is here. In the back, we have the observable, which is a custom observable using the observable API. You can create custom one. This is just read from the current file system. I have a folder with some tickers here, which is few random from Amazon, Microsoft, Facebook, and so forth. And read in memory and start to loop and push all the information of the stock data out to a stream, right? To simulate a stream. So the program here, I read the file here, which means pass the file to the observable stream. I group by the stock symbol, okay? So I group by the stock ticker. Then I merge together by that group and subscribe to update a chart, okay? So let's run this code here and see what's going on. Okay. So we have the console on the side that is printing the stock ticker as a change, and the right side the chart. But you can see that sometimes it blocks. And it freezes, and maybe restart. And sometimes just spike for a little bit, and so forth, right? So what's happening here? Well, the problem is that the consumer who read in memory the data is keep pushing to my stream analyzer, in this case, the link expression, the reactive link expression. And the consumer is slower than the producer. So in this case, the problem is that my consumer is blocked because the buffer, it doesn't handle all the messages, right? It overflow. So how we can overcome this problem? Well, for instance, we can throttle. We can say, well, give me the messages and throttle them every 20 milliseconds, okay? So it's a bit better, but check it out. Well, there's something's missing here. So what's really happening here is that it turned out that actually throttle in reactive extension is destructive. What does it mean is that if you put like 50 milliseconds, only the last message that happened that 20 or 50 milliseconds is going to be received. The other going to be dropped, okay? And that's not really what you want. So how can you overcome this problem, right? So as I mentioned, let's say they have like the consumer produce like 5 messages per second and the consumer only 1. So we have this kind of discrepancy between velocity. As I show you in a demo, reactive extension doesn't have anything built in that handle back pressure, so it just fill up the internal buffer. At one point, the buffer overflow. And if you use like throttle or buffer or sample, there are other API that can help. But anyways, the messages are dropped. Well, definitely you can increase the memory as much as you can, but at one point you're going to reach the limit. You're going to buffer out, and you're going to have out of memory, okay? And that's not definitely what you want. So before jumping in a solution, briefly about the actor model, which is what is based also Akka streams. So actor model is a unit computation, independent, they do some work for you. It's only message passing, so you can communicate between actors asynchronously. And it's composed by the mailbox, which receives the messages asynchronously, process one message at a time, and the other incoming messages are just buffers, so they're not lost. The secret of the actor model to be such a great concurrent programming model is that internally the body, the behavior that you apply, is single-threaded, so you don't have any concurrency pitfalls such as race condition, deadlock, and so forth. And the benefit about the actor model, it came also bring on the table infrastructure such as supervision, which is very handy later we're going to see in Akka streams, because if something go bad, well, the system is able to self-heal and bring back in shape it was in the beginning, right? Think about, I like this example a lot, about the rental car. So if you drive around your rental car, you broke your rental car, you don't worry to fix the car. You just call the rental company and send you a new car, a new actor model, which means that you need to worry about use try catch, block, or handle exception. You just let the system crash, and the infrastructure going to bring back the system it was in shape from the beginning. So this is the characteristic the actor offer. So high availability, scale out and scale up. And this is very important, especially in Akka streams, because when the streams start to flow in faster and faster, well, it's able probably to spawn other actors, not in the same process, but out the process of different machine, and distribute their work to load balance between the consumer and the producer to respond to a high volume of requests or events. Is asynchronous, which is the key fundamental. We're going to see is a part of the reactive stream sort of manifesto. But there is a little problem. So from actor to reactive stream, so I personally experience with the Akka streams, but in .NET, and this apply also to Akka stream for the JVM. So the Akka stream specifically is based on the actor model, from the Akka actor model, right? But it turned out that to build very simple pipeline to flow the process and stream event, you can use actor model, but there are some limitations. So what are these limitations? First of all, actors do not compose, right? It seems that dealing with stream, you can send messages or receive messages, but you create your infrastructure or your topology of actor, and when you're defined, it's hard to change it dynamically, right? You send the messages, and you cannot change the direction of the message later on. So whenever you define your system, that's it. It's hard to change it dynamically. I mean, it's possible, but it's very hard and complex. Furthermore, actors do not compose because you think about it, actors send messages, but the method that you use, like post or send, return void, which is familiar with functional programming. To compose two functions, well, you have to have return something, right? The input of the next function must match the output of the previous one. But if you return void, like in C# or Java, well, this is limiting. You can now use as a composition. This is an actor implementation using C#. You can see that the receive job, for instance, is void, right? So how are you going to compose this? Well, you can't. Okay, so what actually if, so the actor model definitely can be a solution for building stream processing, but how are we going to deal with this kind of composition semantic that is missing, right? But what about if we can use a very rich set of API or semantic like link, right? In this case, we have entity framework, that a link that just get a company, filter, order by, select, and so forth. This is a very abstract, a very high-level abstraction over over SQL, right? In this case, what about if we can use the same exactly approach for stream analysis? This is F#, even better with the pipe operator. So really you compose your function and you pass the result to the next one in a very declarative manner. So this is actually Akka stream for Scala. We have, you create a source 1 to 10, then you create a sync, and we're going to talk about sync in a second. Then you create a broadcast, a merge function, and then you compose all this function. Now, Scala is something like F# calling fix operator, in this case, the tilde and right arrow. And really, you can create all your components for the stream processing and put them together, okay? Okay, so reactive stream. So what about if we be able to use the same level of abstraction also for in Akka.NET, right? So really composing a set of high-order primitive And the framework underneath, it takes care for us how create the actor and compose them. But we use a very high level abstraction, right? So really we start to focus no more on infrastructure, taking care carefully how implement the actor, maybe using the single responsibility principle to apply the behavior to the messages, but instead we just use high order composition with this primitive and compose this actor, make the system compose the actor for us. So this is an example in C#. That's where I create, it's very similar to the Scala example. We create a source from an enumerable, 1 to 1,000. I create a flow, and we're going to talk about flow later, but think about, but in this case, a select, which is project, multiply the number, and the sync is just sync for each, apply a function for each of the event that they're receiving. You can see now they start to compose from, via, and to, and I create my blocks and put them together. So this is a graph in C#. It's a bit more complex. I like to think as a graph is a blueprint. It is what we represent what's your stream processing, okay? And the blueprint can change, but you define your blueprint and actually then become also your building block. In the case, we also broadcast, so you create 2 channels of the event, so you split, and then you merge later, and then you create some functions such as count, sum, and so forth, and then you abstract the value for 1 or 2 channels, and then you put them together, you merge it, and you compose them, okay? The last line of code, the flow shape, actually is a class built in that you put your graph component together to create the final graph. All right, so Reactive Stream is as I mentioned, Reactive Stream is an initiative that pretty much the same company that announced that embraced the Reactive Manifesto last year. They start this organization, right? They define what property stream processing should have. Some of these companies, such as Netflix and Twitter, and they start to define the characteristics, such as asynchronous, which is really the secrets, like no blocking. The process to be asynchronous to ensure the communication across boundaries of the system. It could be to the network, to the CPU, but it must be no blocking. Elastic, well, is important to handle back pressure, right? So this is needed when you produce more and more data, the system can expand and create more actor underneath it for you to be more responsive. And of course, back pressure handling, which is really the secret, what makes stream processing so powerful. But so how this back pressure works, right? How we can get all the data synchronously across the boundary without running out of memory. So it turned out that they created some sort of bidirectional communication. So instead to be only pushing, it was the reactive extension that we saw earlier in the code example, it created some extra interface we're going to see coming shortly. And what it does actually is able to make the producer, the consumer, always interrogate each other and level the work between the two. So if the producer, it becomes faster, while the consumer, it tells the producer to slow down. On the other side, if consumer is able to handle more event, it sends a request, give me more data. At this point, this communication is really push and pulling. Okay, so the idea here really, the push and pull is the secret, really, and what it does really is switch automatically between building block, right? For instance, we have a publisher and subscriber, but what is pretty interesting is that even if I have multiple subscriber, well, the handling, the pulling, pushing between publisher and subscriber is independent. In this case, the 2 subscriber, well, the rate and how they handle event stream can be independent, and the communication with the publisher can be independent. So all the rate, how they handle the event stream, can be completely autonomous. So this is the 3 interfaces. So you can see how similar the first two, the iPublisher and iSubscriber, are with the React extensions. I show you with the embrace the iObservable pattern. However, the iSubscriber have one extra method, which is the onSubscribe. And what it does this is that the publisher give an iSubscription type, which is a typo there, but is iSubscription type to the consumer, which now have the last interface and app subscription, which is access to this method called request, okay? And the request is what the subscriber is using to communicate in a pooling manner, communicate to the producer if wanted more event or less event, or the rate that is able to handle event stream. So during the connection, the publisher, the subscriber subscribe to the publisher, and the connection, the publisher send an unsubscribe notification to the subscriber, which produce, start the communication between the two parties. And as you can see here, the publisher send to the elements to the on next, and the subscriber actually also the request send a notification to request to the publisher to send how many events he wants to receive. And of course, we're on complete and eventually on error if you want to. This is a slide that a test that actually Aka from the JVM did, but it's interesting. I want to show you how they test the back pressure between producer and consumer. And we're testing increasing or decreasing the velocity of the producer, and how the consumer was able really to dance together and coordinate the consumption of the event pretty much in the same rate. All right, Akka Stream, so raise the level abstraction over Akka.NET. Right, is a library that process and transfer the sequence of element using this using bounded buffer, but in a controlled manner, right? So is a space control, and Compose is able to provide the certain API that allows you to compose any kind of stream processing topology. So if you think about, as I mentioned earlier, the actor model in Akka.NET is reactive compliant, right? You can build a reactive program using the actor model, and really Akka Stream is I think the organic, passing to the way how you're going to build a stream processing using the actor model underneath it. And also this Akka Stream is able to leverage the push and pull model, really this bidirectional communication, really, swimming across the stream to communicate to the publisher to tell slow down or produce more event. So a little bit of lexicon. We have the Akka Stream, we have the source, which is, like you can imagine, is where the data are coming in to the stream processing. And then we have the sink, which is the last part of the pipeline, where there is some sort of side effect. Something happened there. You can write to the console and do whatever you want in the end. But it's really the last point of the pipeline. It's like void in C# or Java. The flow is all the components that stay in between, all the transformation, all the stream processing. It can be filtering, grouping, or project with select, element. Pretty much all, if you're familiar with link, pretty much all the same API are available. Then we have a runnable graph and materialize. Runnable graph is, as I show you, is like the blueprint when you create all the group or your component and you compose them together. A materialize is pretty much what you need to materialize the stream. Think about, this is some source that you can create using Akka Stream. We have the from enumerator and other few, but there are quite rich set to API. The sink, that's when you can produce some sort of side effect. We have from first, last, and so forth, the for each parallel. But remember, all these API are asynchronous and not blocking. In the flow, this is really much represent the core where all the transformation happen. So stream materialize is the way they actually think about when you create your blueprint, your graph. Nothing really happens until you tell the system to materialize. Think about the way that think about the blueprint as a lazy evaluation, like in link, right? And you materialize it like how? Maybe called toLink to array. They pretty much exactly work in the same way. In Akka streams, you have the your stream processing, you create your actor system in Akka, and you call it materialize passing your system, and you call materialize. At that point, the system starts to produce the event stream, and the consumer start to consume them. All right, so I'm gonna skip the case study, and let's jump in Visual Studio and see some code, okay? So I have the code example here, I use Twitter, but I think I'll be in a nicer way than the classic example. So I use I'm gonna have a few examples. In the last one, we're gonna branch and broadcast the tweet source. We're gonna have one channel that print in a console as a classic, but the other one we're gonna have some sort of real-time emotion analysis. So based upon the tweet coming in, we're gonna see the average of people that are happy or unhappy or indifferent. Okay? Pardon me? So, so I create, I think, 200 meg tweet in a local file system. I never align the network when I do presentation because I'm worried that it doesn't work. But I have, and that's a good point because actually actually is a good point. What is interesting is that if you work with the real-time data, you also, the fact that you can ask for as many events from the API, but until they're gonna cut you down because you probably ask too much and you fill the bandwidth. When you have like local system like this one, actually you can really test a very heavy, payload of stream coming in because now you can read the file and keep pushing without, wait that the API allows you to get another request online. Yeah, that's a good point. Okay, so in fact, I use the cache tweet. There is also the online, so you can download the code and also play with the online version. So I create an actor reference passing 100, which is the buffer I want to create until the back pressure kick in, which means that you receive 100 event to analyze, and there is any event that go over the buffer, the back pressure, which is a bidirectional communication, is start to kick in and start. So the graph, there are a few here. Let's start with a simple one until we go to the tweet analysis, emotion analysis one. So the simple one here, you can see I create a flow crate. The format tweet is just a bunch of utilities. So just show you for once, it just do some pretty printed in a console, okay? So it's not really fancy. I create a sync, which is, as I said, the last part of the pipeline, and start to print to the console the output of the event analysis. So this is pretty simple. So the idea is that I got the tweet, I format and make it print and print it to the console. So let's run this example here. So it load him in the tweet from the local file system and start to produce the output. Okay. So you can see here, the line here define each tweet, and I get the coordinate, which is important for the next example. But you can see how pretty high rate analysis. The broadcast here is a little bit different. So they'll be more interesting. So what I do here, I create a broadcast, which means I created 2 channels, okay? Let's make a line here. I create a 2 channel. And then I create also merge that I use later to merge back together. If you remember from the chart, from the slide, I have two different lines, right? So the first one, a broadcast, I take the first channel here, I create a select, I return the create byte information from the tweet, and I pass a function here that just create a flow that apply some pretty printing. And then I merge to the channel. The broadcast here, the second channel, instead just do the same thing, but they coordinated and merge together. So as you can see here, I put together in a graph that then later is used as a blueprint to start the materialization and produce all the event. And here I just put everything together. Whenever the coordinate are different than null, because there are some tweets that they don't allow or they don't want send the coordinated, I'm gonna filter them out using the where clause, and then apply my graph here and apply the write sync, which it just does some printing in the console. Okay, let's grab it here. So you can see now, actually, it's interesting that you can see the rate here of the one channel that produce only the user, the create by, and the channel that return only the coordinated are pretty much in sync, one after the other one. Okay, so they're no alternate or they're not stop. They really are merged together because overall there is only one source of event stream. Okay, so they're able to merge and coordinate the work as split and merge together. All right. Let's run it this way. Well, let's check the code first. So this is a bit more interesting. We have a weather API here that calls asynchronously. And what it does here, it grabs the coordinator for the tweet and just interrogate a weather channel to check the temperature. Now, you can see here I have two channels, but in purpose, I use throttle 10 in one channel and throttle 1 in the other one, which means that the two channels are working in a different speed. So what do you think is going to happen? Any thought? You're going to be run all 1 per second, 10 per second, 5? Not going to run? Okay, let's run it first. So okay, the first few are buffer. What's happened here is because there is only one stream of event, well, it's going to run with the lowest rate one. So in this case, even if I have one stream that is very fast, it's able to back pressure that very fast stream and event and coordinate the work with the slowest one. So in this case, we have all running at 1 second, okay? We're almost out of time, so I just want to show. Let's go to this one here. So this is the same example that I showed you, but now I have enabled buffer 10. So this line of code, it means that now I have two channels, one run faster 10 events per second, another one only 1. So I'll be able to back pressure my event stream in a lower rate. However, to overcome the fact that there is one channel that is lower than the other one, I can buffer by 10. So let's see what's happening in this case. Okay, you can see that now the two channels are working in parallel, okay? So we have almost independent analysis here. So we have one channel that analyzes, the 10 event every second, and the other one that it buffer the 10 and produce the result. Okay, so the last example with the Twitter analysis here. So this is a let's run it first. what it does, it real-time get all the tweets and use an algorithm to figure out the emotion of the tweet. Okay, so on the right side we have this chart. You go, the blue one are the unhappy. Unfortunately, we have more unhappy people than the happy one, which is the yellow one, and the red one are indifferent. And then with the console here. So you can see the two streams actually are working at a different rate. So how the code works. So in this case, I have, so I use the Stanford library, which provide some sort of analysis for natural language processing. In this case, actually, they have already a library called Sentiment that I can load up and use to analyze the income text and do all the tokenization and everything for me, which is quite nice. So in the end, it also give me a result, a threshold that can go from 0 to 4. And this is the threshold to indicate the level of happy or unhappiness of the tweet. So I run just the algorithm, grab the result, I use like a switch testament to figure out is a happy or unhappy. I create a chart here, and here pretty simple. I just run the analysis, but in this case, I have an actor underneath. I create an actor underneath it that is one that produce the work for me for the tweet emotion analysis. Okay, so actually I plug in an actor in this case using the AkaStream SPI, which is quite convenient. I think it's called actor process. But yeah, so that's processing. It takes a bit longer. So the consumer definitely is lower than the producer. So in this case, we're able to handle. If you remember from the original example with the React extension, where the UI was blocking, here actually we see it worked quite well. Well, now it's blocked because I think what's happening is that I already analyzed all the tweets, so they start to reanalyze so the value doesn't change. But I can rerun it. Quick. All right, we are 50 seconds to go, and I can start to answer any question you have. Almost done here, really, the last slide. Any questions so far? So you can see actually how the UI, you really move way better without blocking compared to the React extension, because now I have all the back pressure built in, the control, the different velocity of the producer and consumer. All right, we had the demo, and of course we went in the movie, so I decided to put this full. But if you have any question? All right, I am gonna tweet about the slide in the code sample, so you'll be able to download and play. By the way, how many of you are .NET developer, so more familiar with the Microsoft? Okay, okay, everybody, perfect. So yeah, so that's gonna be pretty easy for you then. Just download it, apply it, and run in Visual Studio. All right then, that's it then. Thank you for coming.